The mathematics of predictive policing. Predictive policing applies quantitative analysis to identify likely targets for police intervention and prevent crime, allowing for effective police resource allocation to areas where crime is deemed likely. It uses statistical models to move beyond simple retrospective hotspot policing, forecasting crime through an analysis of change over time. Geolytica, a pioneering, very common predictive policing platform, uses an epidemic-type aftershock model, originally designed for earthquake prediction, and the reaction diffusion model, used typically for predicting chemical reactions, to inform the predictive policing algorithm. The reaction diffusion model imagines motivated offenders and potential victims, animate or inanimate, as activators, and law enforcement as inhibitors. It aims to model the formation of crime hotspots, controlling for relevant parameters and cascading effects. To demonstrate the basics of this model, we have these two formulas. S is a coordinate on a plane with evenly spaced points representing the activators, and t is time. A sub S of t represents the risk of victimization at a specific time. A sub S to 0 is a constant, and B sub S of t is a dynamic value that models the probability of repeat victimization soon after the initial victimization. So this first equation means the risk of victimization at a single place and time equals a constant environmental risk plus the risk of re-victimization. This next formula represents how dynamic risk changes over time. Omega represents a period of time in which a repeat crime is likely to occur, and theta represents how much a crime affects future risk. So this equation states the dynamic risk over time at a specific place equals the dynamic risk times the rate at which it decreases over time, plus the number of crimes committed at this locale during this time, multiplied by how much these crimes affect future risk. The epidemic-type aftershock model originates in seismology, describing earthquakes as self-exciting, where a parent earthquake will lead to aftershocks, creating permanent and temporary earthquake hotspots. The EAS model posits a random parent crime has a cascading effect which leads to more crime. Policing areas are separated in boxes N. In this model, first-generation events happen randomly at N at a rate of mu. Theta represents the average number of crimes caused by these first-generation events. Lambda sub n of t represents the predicted crime rate in box n at time t. Mu sub n is the background crime rate in box n. T sub ni is the time of the ith past crime in box n. Omega is the rate at which a parent crime loses influence. So this equation states that the predicted crime rate at a specific time and place equals the background crime rate of that place plus the sum of all previous crimes in that place times the exponential decay of influence of these crimes over time. This means that after a crime, there will be a surge of aftershock crimes, increasing the crime rate, but that influence decreases over time through intervention. Predictive policing is often criticized both mathematically and socially. Synthetic population bias is a statistical issue where police use their own data to inform the algorithm, which may not be indicative of actual crime trends. It is also vulnerable to runaway feedback loops, where they police a specific area more because the algorithm predicted a higher crime rate there, and they therefore find more crime there, and the cycle continues. There are also social concerns regarding over-policing minority communities, building a surveillance state, and the tendency of these systems to cement racial bias through self-reinforcement.